and welcome my wonderful honors students to your first major introduction video for your honors physics class. This is Mr. Jockmans here. I'm going to be doing a little more about dimensional analysis and a lot about uncertainty. But while we begin, I want to say welcome. These videos are to help prepare you for the next day's activity, lesson, or lab experience. And while doing this, I have some expectations for you. I do expect you to have your notebook out and take good notes on what you're learning here. I expect you to answer the questions posed and write them down. There's going to be one at the end of this video. If I'm going a little too fast or you kind of didn't really get something, feel free to pause, rewind, or do whatever else you need to learn. And because of that, you may not be ready now, but soon, hopefully, you'll feel comfortable enough to come tell me things you didn't get, things you didn't understand, or things you need to improve in the videos, or things you want to keep seeing. We're all in this together, and this is made for you. So I have a couple goals for you. This video will reinforce the idea of dimensional analysis, as well as introduce you to a new idea. We're going to discuss, again, how to use dimensional analysis in order to solve complicated situations, what the idea of uncertainty is, and finally, how to actually account for it when you take measurements. So to start us off, now at this point we're going to do a dimensional analysis situation. This is a pre-topic that gets a lot of use in physics in our class. All the topics you're going to have the entire year are going to deal with converting between one unit and another. Common conversions will be kilometers per hour to meters per second, centimeters to meters, kilometers to meters, and kilowatts to watts. Both are the exact same in terms of the amount. And you're going to do some other ones later on that may include calories to kilocalories to joules, joules to kilowatt hours, nanometers to meters, and a bunch of others. So with this dimensional analysis stuff, I'm going to do kind of a decent example here. If you think you've got it, feel free to skip ahead to the next slide. If you're unsure after this, I have a video linked in the PB Works that will really help you out. So here we go. How many centimeters are in 1 mile? The major idea, we're going to start with 1 mile, and we're going to end up with how many centimeters there are. So we start with 1 mile. I put it up, and I'm going to use my first conversion. I'm going to look up and discover that 1 mile is 5280 feet. I'm putting 1 mile on the bottom of this fraction, so that way this and this mile will cancel out when they multiply. The units cancel. When that happens, you're left with feet. Next up, I'm going to do again feet on the bottom, so the feet and this feet cancel out. Left with inches. Multiply again by looking up the number of inches per centimeter. The miles cancel, the feet cancel, the inches cancel. I'm left with centimeters on top, which means that is the end unit I need. Since this on top matches this over here, I am now done. I multiply 1 by 5280 and times 12 times 1. And then I write that number. On the bottom, I do 1 times 2.54. Everything on the top together divided by everything on the bottom together will give you a correct answer in the units you need. Look at the colors, they cancel out. I then check, is centimeters what I wanted here? How many centimeters? Looks good. Again, if this is a little bit too quick or you're still a little unsure, look at the wiki for more information. Now let's get to the real stuff for today, uncertainty. Basic uncertainty in measurements involves devices having limits to their ability to measure. In other words, stuff cannot be as precise as we want. A common example are watches. Here's a cool expensive watch. Notice it only has got the 12 numbers that represent the faces. Here's another one. This watch can tell you the hours, minutes, and seconds. What we're going to say now is that each instrument that we use to measure things has got an instrument least count. This is like the smallest unit it measures. So, with these two clocks, the one on the left, the smallest time period you can know for sure it is 5 minutes. The difference between this mark and this mark is 5 minutes. This one, however, you can know exactly what time it is up to a second. You don't know if it's 37.5 seconds, 37.8 seconds. But you know for a fact that the smallest number this could read off is 1 second. So here we are. The instrument least count of 5 minutes, instrument least count of 1 second. This clock is way more precise than this clock. So when it comes to rulers, the same thing applies. Look right here. There are a bunch of marks up to 1 centimeter. This is the smallest count that this has, which means its ILC is 0.1 centimeters. Every mark represents 0.1 centimeters. So other ones could have half a centimeter. Those are the ones that just have this mark in between 0 and 1. Or 1 centimeter. All it has is just this mark and the 1 mark. Obviously, the lower your ILC, the better instrument it is. And finally, when it comes to uncertainty, we use it mathematically a lot in our class and labs. Here's the key point. You're always going to go 1 decimal beyond what you can actually measure in an instrument. So here's an example. You could see that this thing on top is what we're trying to measure. Here's the ruler. This thing is in between 3 and 4 centimeters long. The ILC is 1. So we know for a fact it's 3 point something. 3 point something. 1 digit beyond that is unknown. I don't know if it's 3.2 or 3.8. So those are all guesses. So the correct uncertainty here would be 3.1, 3.2, 3.3, blah, 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 3.9. A guess of 3.45 is technically wrong, because that means we know for a fact it's between 3.4 and 3.5, because the last digit is always the guess. And looking at this, there's no way you could tell it's between 3.4 and 3.5. All right, you try. What I expect from you now is to take a look at this thing and come up with an acceptable measurement here. At this point, you should pause the video and then restart it when you think you have an answer. All right, so looking at this, 3.1, 3.2, 3.3, 3.4. It's between 3.3 and 3.4. So the correct answer will be 3.3 something. I guess 3.38. So if your answer is 3.31, 3.32, blah, 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 3.39, then you are safe. If it was not, if it was 3.3 something something, you technically were too precise and you were wrong. With that being said, that is the basis I need from you for day 2. Come up with your questions, concerns, and you should be golden. Thank you very much and have a great day.